We're going to start, as of today, until the end of the semester, we're going to talk about essentially digital work. We're going to introduce sampling theorem and kind of show how you can go from continuous world to a discrete world, even more from the discrete world into numbers, and do all the signal analysis and signal processing using pure numbers. Why is this important for us? Because we live in the era of very powerful computers, right, and digital signal processing. And pretty much all of our signal processing is moving in that direction. We actually, in all, let's say, communication systems, control systems, pretty much all linear systems, what we strive to do is to digitize everything as soon as we can and do all the processing inside our computers. And the reason is because the hardware, or DSP hardware, is very cheap, it's extremely powerful, and it allows us to do the things that we cannot even attempt to do in the analog world, with everything changing with temperature, with aging, and exposed to all of these drifts over time. So what we're going to do today is just review sampling theorem. I'm sure you've seen it before, so I'm going to be relatively light on math, but try more to explain what it means and how it works, and maybe give you a different perspective. So sampling theorem. Precursor to sampling theorem is a notion of band-limited signal, right? Sampling theorem applies only to signals that have this property, which we call band limit. So let me define it first. Signal x of t is band limited if x of f is identically equal to 0 whenever f is larger than some b. B is what we call bandwidth of signal. D is the bandwidth of the signal. And this x of f is, of course, is the Fourier Transform of x of t. So what is it that we're talking about here? Remember how our, this is now f, and this is the magnitude spectrum, x of f, of our signal. Typically, our signals that we routinely process are what we call baseband signals, meaning they occupy certain band around the origin, and then they kind of have spectrum that falls off as you go further and further in the frequency domain. Sometimes, theoretically, this goes to infinity, but we've learned that this is in our control. We can always find out what is the value of B, so that the percentage of the signal power that is captured between 0 and B exceeds some threshold. And we define the bandwidth of the signal based on the threshold. We can define 99% bandwidth, 99.9% bandwidth, 99.999. You give me the number, I'll tell you what the bandwidth is. But that's a solvable problem, right? And we always do. So this, we actually, if the signal is not band limited, which some of the signal might not be, then we actually force it. And how do we force it? We typically, before sampling, put a low-pass filter that will actually do this. Cut the portion of the signal that we care about and reject everything else. Let me give you an example. When I speak, what I produce in the frequency domain extends to several, let's say, several kilohertz. Now, what you hear, it goes up to 16, 20 kilohertz. So is there any reason for me, if I were to send this signal over some communication link, to keep anything above 16 kilohertz? know, because even if I reproduce it to you, you're not going to be able to hear it. It goes even further more. If you look at my speech signal, 99% of its energy or of its power is within a 3.4 kilohertz. So up to 3.4 kilohertz carries 99% of the signal power. So what we do in telephony to save the bandwidth, we get rid of everything above 3.4 kilohertz, right? And we preserve signal pretty well. You know when you talk to somebody on the phone that you can understand them, and majority of the signal is being preserved. There is some difference, right? And you all are aware of that. If you talk to somebody on a telephone, their voice sounds different. And you have to actually, when you talk to them for the first time, you would always say, who is this, right? And then you get accustomed to somebody's sound of somebody's voice over the telephone. The reason for that is, this is how let's say your voice signal might look like, but this is what we do. We cut, some high frequency components out, and that's what colors. And you can always tell that you are talking to somebody on a telephone versus talking to them in person. But that's a trade-off that we make, and we do that deliberately because that saves us a bandwidth and allows us to put more users on the channel and charge more money and become more efficient and economical. So nevertheless, going back to the story, for every signal that we're going to sample, the first thing that we need to know is what is the signal bandwidth. Right? We understand that the signal has to be band limited, and the question of point of interest here would be what the signal bandwidth is. So knowing that, let me state the sampling theorem. So it says consider x of t, which is band limited. With a bandwidth of b. Then what the sampling theorem says, x of t can be reconstructed from its samples taken at uniform sampling rate Fs that's greater than 2 times b. So how do I understand this? Well, here's what this theorem states. Let's say this is t. This is my x of t. When I look at it this way, x of t is continuous function of time. So it appears that if I were to know what x of t is, I need to know all of these points and the points in between, right? Because it's a continuous function of time, and if nothing else is said, then by knowing this point and this point tells you nothing about what's in between, right? That is how it may look on the outset. The key differentiator here is that this is a band limited signal. So we have the x of f that only exists between some minus b or up to some frequency b. So what does this do practically? Well, this tells us, you remember that what is this related to? It tells us what sinusoidals this signal is built on. So if I limit the sinusoidals at the high frequencies, what I'm effectively limiting is how fast this signal can change, right? Because if I say this signal is built only up to sinusoidals that go up to b, then it puts the limit on how fast the signal can change. because in order to build the fast changing signals, I need a high frequency sinusoidals. I cannot build, very detailed, let's say, image by using bricks that are this big, right? So if the bricks are this big, that kind of tells me how fine the detail of what I'm building can be. And if I'm taking out all of these high frequency components, then I'm actually limiting the ability of the signal to change. So at some point, if I know what this is and this is, that kind of uniquely tells me how these 2 points need to be connected. And that's this theorem here. What is important here is not that you are approximately reconstructing the signal. The signal is reconstructed without any loss of information, so you're getting exactly the signal itself. So how do I understand the processes of sampling theoretically? Well, this can be understood as a multiplication, right? I can see a sampling as a multiplication between the actual signal and the sampling sequence. Sampling sequence, I'm going to define like this. It is going to be a series of delta pulses that are separated one from the other by Ts. Ts is 1 over Fs. Ts is 1 over Fs, where Fs is the sampling rate, which I claim needs to be 2 times larger than the bandwidth of the signal. And then the whole process of sampling, I can theoretically see like this. I have my x of t coming in, and I'm multiplying this with delta t of t to get my sampled signal here. I use x bar of t as a sampled version of the signal. So let's let's try to explain what is happening here. First, I'm going to try to find out the Fourier transform of this one, right? I understand the process of sampling in a time domain. It's very easy. It's the multiplication of x of t and this delta t of t. But what is happening in a frequency domain? So let's look this, and I have 2 ways how I can look at this. One is straightforward, and it's very easy to show, but it carries limited insight. I just derive it, and it's a nice formula, and it looks how it looks. But then the other one is a little bit longer, and but it should be very easy for you to understand. And what is better, gives you exactly the insight in what is happening when you do the sampling. So let me first do the first one. So Fourier transform of sample signal. So if I look at f of x hat of t, I can say this is a Fourier transform. X hat of t is the product of these two, so it's x of t times delta t of t, which is equal to Fourier transform of x of t times sum when n goes from minus infinity to plus infinity, delta of t minus n ts, right? This is the sampling sequence, just a whole bunch of pulses that are coming ts seconds one after the other, right? There's infinitely many of them. And here, I can write this as a Fourier transform of sum when n goes from minus infinity to plus infinity, x of t times delta of t minus n ts. But now, what do I know about these delta pulses? Delta pulses exist only at discrete points in time. Everything in between is essentially equal to 0, right? In between these 2 delta pulses, everything is equal to 0. So when I multiply these 2, this 0 will make 0 times anything is 0, right? So this is essentially the same as saying Fourier transform of sum when n goes from minus infinity to plus infinity, x of nts, right? times delta of t minus nts. Because everything that is the function x of t that is outside of these delta pulses might as well be 0. So I can just say these discrete values are what matters. Now if you look at this sum, it only has one function of time, which is what? Which is this delta. So if I bring the Fourier transform inside, it operates only on delta. What is the Fourier transform of delayed delta? What is the Fourier transform of delta? 1, and then because it's delayed, e to the minus j and ts. So this becomes sum when n goes from minus infinity to plus infinity, x of nts, e to the minus j and okay? So that's the Fourier transform of the sample C. Looks like any other formula, right? At this stage, I don't think you see anything special here, right? But let's take a different approach to understand. There's actually what is missing here. J, F, and Ts, right? Okay. Let me do one more. 2 pi F and Ts. Okay. Now it's there, right? So let me see this differently. First, let me look at this delta P of t. And this is sum when n goes from minus infinity to plus infinity, delta of t minus nts. What can you tell me about this function? Is this a periodic function? Look at it over there. Is it a periodic function?
Yes.
What's the period?
Ts.
Now, when you say it's a periodic function, what's the automatic gut response? Fourier series, right? So this has a Fourier series. As a matter of fact, is it even or odd? Even, right? So not only has a Fourier series, all the sign parts are equal to 0, right? What's the DC value? Okay, what I'm going to do is I'm going to integrate over one period, right? So from here to here. What's the integral? What's the area under this delta? 1 divided by the period 1 over NTS, 1 over TS, right?
Yeah.
That's the DC value. So I already kind of know here A0. So I can first start by saying delta T of T is equal to A0 plus sum when n goes from 1 to infinity, an cosine 2 pi n f0t, right? Where, well, let me just say fs, because the period is, fs is equal 1 over ts, right? The central frequency, right? Now, a0 is equal to 1 over ts, and then an is going to be integral 2 over ts, integral over ts. I can just put this delta t of t times cosine 2 pi n fs t dt. So to calculate this, I'm going to say this is 2 over ts, integral from minus ts over 2 to ts over 2, delta of t, right? Because it's in this interval here from minus ts over 2 to ts over 2. This whole function delta t is just a simple delta that sits at the origin. So delta of t cosine 2 pi n fs t dt. And there's nothing easier than integrating delta functions. So what is the value of this integral? Just the value of the subintegral function at 0, right? Because everything else, everywhere else, this delta is equal to 0. So what's the value of the cosine at 0? 1. So this is 2 over ts. So look at this Fourier series now. Delta t of t is equal 1 over ts plus 2 over ts. Sum n goes from 1 to infinity cosine 2 pi n fs t. Okay? So that's the Fourier series associated with this sampling function. So now, let's take a look at what the sampling does. So here's how I see my x bar of t, which is the sample signal here. It is x of t times this delta t of t, which is x of t times 2 over ts, oh sorry, 1 over ts, plus 2 over ts, sum when n goes from 1 to infinity, cosine of 2 pi and fs t, right? So that's just what the sampling is. So if I expand this a little bit, this is 1 over ts times x of t plus 2 over ts, sum, n goes from 1 to infinity, x of t cosine 2 pi and fs t, okay? Now let me take the Fourier transform of this. X bar of t. What's the Fourier transform of the first one? It's just 1 over ts x of f, right? Plus 2 over ts, sum, n goes from 1 to infinity. What's the Fourier transform here? It's going to be 1/2 x of f plus nfs plus 1/2 x of f minus nfs. Remember? That's how do we call this property of the Fourier transform? Modulation. Modulating property, right? And then just to be cute here, I can cancel these. You can see that right away. And then this goes from 1 to infinity. But do you see that I can rewrite this whole thing as 1 over ts, sum over n goes from minus infinity to plus infinity, x of f minus nfs. How is it that I'm writing this? Well, look at the first, let's start with the first term. This one I can obtain for n equals 0. See, when in this sum here, when n is equal to 0, this is 1 over ts x of f. So that covers this one, right? Do you see that? No. Let me expand this back. So this goes 1 over ts up front, x of f plus 10fs, plus x of f, there's a dot, 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 right? X 9fs, plus and so on, plus x of f, then plus x of f, minus fs, plus x of f, minus 2fs, plus and so on, right? Up to infinity. Do you see this? Yeah. That's this expanded, right? Now, look at this guy. This corresponds to this guy, right? These guys, when n is positive, corresponds to these terms, right? And then the terms when n is negative correspond to these terms. So you can see that this is this entire summation upstairs. So this is yet another formula. Why is this one better than this one? Well, let's understand what this tells us. So if I were to draw this, let's say this is f. This is my, and I'm just going to kind of draw it like this. This is minus b, b. This is my x of f. Okay? Now, if I sample x of f, I get this x bar of f. So how does the x bar of f look like? This is f. This is the magnitude spectrum of x bar of f. This is 0. This is ff. This is 2fs minus fs, and so on. Right? That's sampling frequency. So I get, according to this, I get my signal back. So this x bar of f contains the original signal. It's just now scaled by 1 over dx. Let's assume that this was some sort of 1. Okay? Then I get the same version of the signal, but shifted to fs, 2fs, 3fs, 4fs, and so on. So what sampling in a time domain does is it performs the periodic extension of the signal in the frequency domain. Right? So if you look at the sampled signal, the Fourier transform of the sampled signal is this. You take your baseband signal that you're sampling, you take its spectrum, and then you start repeating this spectrum centered around the frequency of sampling. Nowhere in here did I put, neither in this derivation or this derivation, I said anything about the relationship between fs and b. This is always true. This part is always true, regardless of what the relationship between these two is. But from this picture here, it becomes obvious that in order for this signal here to have these so nicely separated, then this needs to hold. Fs minus b needs to be greater than b, all right? Because if it's not, then you start overlapping between these two, okay? And this gives us a condition that Fs needs to be greater than 2 times b, okay? So here's the fine point that you may kind of not always understand when you read sampling theory. Sampling is always possible, right? You can sample at whatever rate you desire, right? Now, what you're doing by that is you're performing the periodic extension of the signal in the frequency domain. Now, for the signal to be reconstructible, you need to satisfy Nyquist criteria. But you can sample at rates that are not satisfying Nyquist criteria, but maybe the shape of this spectrum is maybe such that it permits that to happen, and then you can interlace them and do all sorts of interesting things. So what is it that we showed here? We showed what happens to the signal that is sampled in a time domain. What is the equivalent of sampling when you look at it in this other world, in the frequency domain? And what is the answer? Sampling in time domain is the periodic extension of the in a frequency domain. Okay, so that's the view that we need to understand. Now, before we actually, we'll come back to that, but let me just ask you this. If I'm presented with this signal, and my goal is to come back to this guy, how do I get my original signal?
First,
Low pass filter. The easiest way is to put the low pass filter here and get rid of all of these high frequency components, and you're going to get back your signal, right? But are there other ways how you can do it? Can I filter this one and then multiply by cosine of 2fs and bring it back? Right? So there are other ways how we can do it. It's just and it all comes back to this picture. This view of sampling is, in my opinion, the most useful view. I mean, they usually would, in all books, present you with a view of multiplication in a time domain. But from our perspective, to really understand sampling and its implications, this is the view that you should keep in your mind. Now, what is the problem with the definition of sampling? How we define the sampling process? The problem is this guy, right? This guy is not a real signal. Right? Can you generate something that's a delta pulses? No. And how do you see that? If you look at the Fourier transform of this guy, Fourier series, how about these coefficients, right? Are they ever decaying? No, you need all the harmonics up to infinity, and all of them have the same magnitude. So unlike all the other signals where you saw n downstairs and kind of diminishing the powers of the components, this one is unique because the power of the components never diminishes. So what is the total power of the signal? It's infinite, right? Because it has infinite components, each one of them carrying a power, proportional to this magnitude. So therefore, this is not a real signal. So, and we know we sample, right? So let's see how you actually can sample in a practical way. So practical ways of sampling. So let's take a look at it. All right, so say instead of so I use practical sampling. Say that instead of having a delta pulse train, I have any other or some other periodic function, and I'm going to call this Pt of t. This is a, this is Ts, 2Ts, 3Ts, and so on. And then I have pulses that, look like this. That's just an example. It can look anywhere else. It can be triangle, or it can be a square pulse, or it can be any kind of pulse, as long as they're periodic, and as long as they go, as they are, pulses are occurring every Ts, where Ts is that sampling interval. Now, let's proceed in the same manner as we did just a second ago with the delta pulse chain. What can I say about this Pt of t? Is it periodic?
Yeah.
Well, I made it that way to begin with, so it is periodic. But since it's periodic, what do I know about it? It has a Fourier series, so I can say that this Pt of t is going to be equal to, and in general, it may be even or odd, but let's say it's neither one of them. So it's C0 plus some, when n goes from 1 to infinity, Cn cosine 2 pi nfs t plus some theta, right? That's in general the Fourier series. This is the second trigonometric form that we have, right? C0 is the DC component, and you have a whole bunch of sinusoidals that are aligning in magnitude and phase to create this periodic signal. Then the sample signal x bar of t can be seen as x of t times this Pt of t. Right? I can create the sampling just by multiplying these two. And that's not obvious in the time domain, but let's see what happens in the frequency domain. So I can see that my x hat of t is equal to C0 x of t plus some, when n goes from 1 to infinity, Cn x of t times cosine 2 pi and fs t plus theta n. Now if I take the Fourier transform of this, I get that this is C0 x of f plus some, when n goes from 1 to infinity, Cn. Let me just actually follow what I have here. I'm going to say Cn, but note that I have underscored this, making it complex value. Cn, and then over 2, and then modulation property applied to this would give me x of f plus nfs plus x of f minus nfs. And here, this Cn is equal to Cn magnitude e to the j theta. Just a complex coefficient. And then, taking it one step further, you get that Fourier transform of x bar of t is equal to C0 x of f plus some, actually I'm rewriting the same thing, so let me write it in a different format. Sum n goes from minus infinity to plus infinity, Cn complex x of f minus n fx. So now look at this, what is happening here? Well, similar thing to what I had previously. Now, in this case, here's the drawing, right? Your x of f looks somewhat like this. It is between minus b and plus b. It's a band limited signal. And now I sample this with this arbitrary pulse train that has the Fourier series is given by this. And what happens as a result of that, my picture in a frequency domain is very similar. This is 0, this is fs, 2fs, minus fs. Here's the signal here. Then this is replica, this is replica, this is right. This one is scaled by C0. This one is scaled by C1. And so on, C2 and so on. So fundamentally, what is happening is very similar. You're getting a signal that you're sampling in a time domain with this weird looking pulse train that is not a train of delta pulses, but some real pulses that you're able to generate. And what the result of that is essentially the same. You have a periodic extension of the signal in the frequency domain. The only difference is what? Is that these magnitudes are not the same. You don't have the same magnitude of these spectral replica, but that's not that critical, right? What is critical here that you realize that the same relationship holds. This frequency here is fs minus b, and this frequency here is b. So we get also that fs needs to be greater than 2b. And you know, what is the recipe for reconstruction here? How do I get back this signal here? All I need to do is, again, place the low-pass filter here, and that low-pass filter will extract this component here. I may need to do some amplitude adjustments, but that's relatively easy. Okay? So, how do we sample in a practical world? You cannot get deltas, right? So you have to sample with some other pulse trains. The most common one is like square pulses, right? Not the delta pulses, but sampling everything with square pulses. That's called natural sampling, or anything else on/off, right? If I can take my signal, this is the most common. Yet another way how you can sample, right? If you look at your signal x of t, let's say this is it, and I can turn it on and off, right? It's on, then it's on. Then here it's on, then it's on. Here it's on, off, and so on. This is equivalent to multiplying your signal x of t with a train of square pulses, right? Because if this is pulse that is 1 when it's on and 0 when it's off, then you can see that the multiplication of these two leads you to a waveform like this. And then the question is, well, is this a valid sampling? And I don't think you can answer that straightforward in a time domain. But in frequency domain, it's very easy to understand. This pulse train of square pulses is nothing but the Fourier series. Fourier series has these coefficients C's, A, C0. So this we very well know how to decompose the square pulses, the Fourier series. And as a result of this sampling, I'm going to get something like this in a frequency domain. That if my fs, meaning that if I turn it on and off fast enough, will actually allow me to if my fs is greater than 2 times p, I'm able to reconstruct my signal back. So, however you get the multiplication of the signal with with a periodic waveform of a proper fundamental frequency, you can actually accomplish the same. So that's the sampling part. Let's look at the other part, which is signal reconstruction. We already kind of hinted it, but let's derive that strictly. And let's derive it strictly, and then we'll see how you actually do it practically, because what you'll find out, just like in the case of sampling, if you approach this theoretically, you are actually hitting a dead end. So you have to do some sort of approximative reconstruction. So signal reconstruction. Here's what we already know and we already hinted. There's replicas of your signal. They're centered around Fs, 0, minus Fs. To reconstruct the signal, I need to put a low-pass filter that will get only the portion between minus Fs over 2 to Fs over 2 go through. So this is X bar of F, this whole signal. And this, remember, this is 1 over Ts magnitude. If I look at it only, strictly speaking, as a sampling using the delta pulse. So my X bar of F is going to be equal 1 over Ts, sum when n goes from minus infinity to plus infinity, X of F minus NFS. This is the sample version of the signal. So it is easy to see that X of F, my original signal, is going to be X bar of F multiplied by Ts times the rectangular pulse of F over 2 times Fs over 2, right? That's this pulse here. It has a width of Fs, and I'm making it magnitude of Ts so that I can cancel this one over Ts. So, if I take the Fourier transform of the left-hand side, then I get the Fourier transform of the left-hand side is just x of t. But it has to be the Fourier transform, same as the Fourier transform of the right-hand side. So, Fourier transform of the right-hand side, which is x bar times of f, or inverse, I should say, inverse Fourier transform of the left-hand side, f over fs. Now, I'm taking the product here in a frequency domain. So what does that correspond to in time domain? Convolutions. What is it that I need to take the convolution of? I need to take the convolution of my sample signal, x hat of t, and inverse Fourier transform of this rectangle. What is the inverse Fourier transform of the rectangle? Sinc. Excellent. So this becomes let me make sure these notes are correct. All right, so I can say this is x hat of t convolved with the inverse Fourier transform of Ts times the rectangle of f over fs. Now this is x hat of t is sum when n goes from minus infinity to plus infinity, x of nts times delta of t minus nts. So that's the sampled version of the signal. And I need to convolve that with a sinc, which is sine, or let me just write it here, sinc of pi fs t. That's the inverse Fourier transform of this one. Now, there's nothing easier than convolving with the delta function, with delta pos. If I take the signal and I convolve it with delta, I get my signal back. If I take the signal and convolve it with delta that's delayed by some amount, what do I get? A signal that's delayed by the same amount. So this ends up being sum when n goes from minus infinity to plus infinity, x of n yes times sinc of pi fs t minus n ds. Okay? And this is my reconstruction formula. How is this different than my sampling signal? Well, what you see here, this is x of t, right? So I'm getting x of t, but the only function of time on the right-hand side is this sinc. These are pure numbers. These are the samples of my signal. So this is not x of t. These are the discrete values of this function taken at the given points. Based on these discrete number of points, I'm reconstructing all this infinite number of points in between. And how am I doing that? Well, I'm using this sinc function as a reconstruction function. This is how I actually weight these samples. So let me draw a picture here, how is this working, right? So here's how you start. You have your samples, and let's say this is where they are. Right? So these are my x of nts, right? All of these samples here. Now, if you look at it this way, it seems on the outset, as I said earlier, that there's many different ways how I can connect these points, right? What out of all of these infinitely many number of ways how I can connect these points, only one will lead me to my function x of t. Which one? Well, I take, according to this formula, let's say for n equals 0, I take this sample here and multiply that by sinc. How does the sinc look like? Well, it is somewhat special because it will be 1 at the very place of the sample, and it will go through 0 at the place of every other sample, right? So it will not interfere with any other sample, right? So then I say, okay, well, what do I do with this guy? I do the same thing, right? So that's the second sinc function. The third sinc function looks like this. And here's where the magic happens, right? You notice that after I'm putting all of these sincs, none of them interferes with any one of the other ones at the point of sampling. If you look at the points of sampling, all of these other sincs will go through 0. So at the point of sampling, I always get exactly what I've sampled there. Where the magic is, what this theorem here, or what this expression says, is that all of these tails that are in between are going to magically add up to this unique function x of t, right? So what will happen when you add all of these tails, they will actually connect to this function x of t in a unique way. And this is how I get my function back. Now, time domain is really, difficult to understand, right? In time domain, I mean, this is very, very, how should I even say? It looks like a magic trick, right? Why would these tails add and all the story that I'm telling? But here, it is extremely easy to see what you're doing. You're actually cutting out all these high-end components and just letting the proper signal go through. It translates into this thing in a time domain, but we know exactly what we're doing. Now, here are some things that I'm sure you already noticed. There are some practical things that are problematic with this formula. What is problematic with this formula? What is it that you don't like? It should cause you uneasy feeling at this point.
0.
Zeros. Why do you don't like 0?
T equals 0.
T equals 0. Sinc is 1 at t. What should bother you here is if I try to implement this practically, right? you see this sample here. It affects all the other samples way, way over here, right? Because these sinc functions are nice mathematically, but just like delta or square pulse for that matter, they don't lend themselves easily to practical implementation, right? If you look at it, this means that this sample here will contribute to tails all the way up to here. This contribution is small, but nevertheless, if you want to be, if you want to be precise theoretically, then you have to take this contribution into account. And we know that this is the same kind of problem that we had before, and that's the problem of causality, right? If you take the square pulse here in the frequency domain, then the impulse response of that filter is sinc function, which is non-causal. So that tells us realistically, you cannot realize the brick filter. You have to approximate. So just like in a sampling, we had to do something about these delta pulses, which you cannot really generate the train of delta pulses. We need to do something about reconstruction here. In a time domain, it's not easy to see what needs to happen, right? What alternative do I have to sync? Well, maybe it is easy, right? And I'll talk about it in just a second. But in a frequency domain, it's very easy to understand how do I go about, filtering with this square pulse. And the answer, it doesn't have to be this good, right? This filter can be something like this, right? It can be good over this, and then it can roll off, right? As long as it gives me enough attenuation towards these other components, I'm going to be fine. And this gives you a whole bunch of practical possibilities for realizing this filter. Anything that is flat across this band to let this portion of the spectrum go through unchanged and attenuates strong enough over the higher frequency bands will do the job. Now, you see another thing right away, that if this Fs becomes larger, then the separation between these components is larger in the frequency domain, and your job in designing the filter becomes easier, right? So there's a fundamental trade-off here between oversampling, which means sampling beyond what is required theoretically, which we call Nyquist sampling rate of 2 times the bandwidth. So there's a trade-off between oversampling and how easy it is to do reconstruction. I mentioned earlier that the bandwidth of your telephone voice is 3.4 kilohertz. What is the sampling rate of the telephone voice? How much do we sample? What's the sample rate for a voice?
60.
No? Well, what is the bandwidth is 3.4 kilohertz. So theoretically, you could sample it at 6.8. But what do we sample it at? I know this, 8 kilohertz. Your voice is sampled at 8 kilohertz, right? And then it's digitized at how many bits per second? 8, right? 8. So you end up, what is the bit rate that represents the voice? 8 kilosamples per second times 8 bits per sample, 64 kilobits per second. So if you think about what runs through your telephone lines, the landline telephone lines, it's 64 kilobits per second. Every time you pick up a landline, although I don't know how many times do you ever pick up landline, but you get 64 kilobits per second circuit. That's called DS0, right? It's like a fundamental thing in the telecommunication.
Is it same like the DSL modem, something like that? 64 kilobytes per second?
DSL modems go much, much more than that. I mean, would you ever pay anything that's 64 kilobits per second, right? You're getting 20 megabits per second DSL modems, right?
Yeah.
And there's a really cool theory how you do that, right? Because remember, those lines were all dimensioned for voice. So now you're taking the voice lines that were meant to handle 64 kilobits per second, and somehow you are squeezing this
20 megabits per
Yeah.
second through these lines, right? And this is not an easy task, and it's pretty cool how they do it, right? And in some courses we're going to go over that. Okay, so once you realize that you cannot do the ideal filter, then you say, well, what are the practical solutions to that? And there are a whole bunch of them. I'm going to actually cover, let's say, one of them tonight. And this is the simplest one. This is zero order hole. So let's say here practical reconstruction. And this would be something that's called zero order hole. Okay? Here's how zero order holes works. You would have your sample signal, x of t, and then we run this through some filter, h of t, to get what we call x hat of t, which is an estimate of my signal at the baseband. Now this signal here, since I'm not reconstructing with sinc function, is going to be different. I'm introducing some error in my reconstruction, but the good thing about it, it's all within a system design control. You have pretty much freedom of choice. You know, if I want this x hat of t to be very good reconstruction, then something needs to go closer to the sinc. If I'm satisfied with the less accurate reconstruction, then I have more freedom in how I choose my filter. In the zero order hole case, this h of t is going to be rectangular of t over ts. So it's a pulse in a time domain, right? If I look at the impulse response of this one, this is how it looks like. Right? So it is the width of this guy here is ts. So this is rect of t over ts. This is t, and this is h of t. Now, this one is very easy to generate in the time domain. Remember, this is the filter that, when presented with delta, gives you the pulse. How does the reconstruction look like here? Well, here it is. Let me draw a picture of the reconstruction, and then we'll write some math to describe what actually happens here in both time and frequency domain. Here are your samples to begin with. They're all coming at 0. This is ts, 2ts, 3ts, and so on. So here's how I reconstruct the signal. I put a pulse around it, put a pulse around the second one, put a pulse around the third one, pulse around the fourth one, and so on. Okay? So you can see intuitively that that kind of builds the signal back, but it's not this smooth approximation, right? It is rather coarse approximation. You have these, staircase things that approximate the signal. Intuitively, let me ask you this: how do you reduce the effect of this jaggedness? If I were to do what? That's a circuit approach, but and we'll explain why does that work in just a second. But when is this effect really pronounced? If I try to stretch these TS's to the maximum limit, right? If I make this TS essentially 1 over 2b, then it has the bigger effect. But if I oversample, then it will have a smaller effect. Do you see that? If the samples are closer, then these kind of tend to become more and more like this. Think of a limiting case. Think of a case where you sample at a really, really fast rate. Then you actually have these pulses that are so close to one another that you need a magnifying glass to see that there is actually jagged line that is behind this
approximation. So two things we already kind of learned just intuitively. One is this works better if you're oversampling, which is fundamental trade-off that we already kind of indicated. If you oversample, it becomes easier to reconstruct. And the second thing is, it seems like you need to do something after you reconstruct the signal. And this is this smoothing that through a low-pass filter that usually has some capacitor to absorb these transitions, you know, from the reconstruction. So let's look at this, since we're now, know all the math associated. Let's kind of put some formulas and see if we can quantify some of this. So this x hat of t, which is this reconstructed signal, can be seen as x of t convolved with the impulse response of this filter, right? Now, this in our world becomes sum when n goes from minus infinity to plus infinity, x of nts times delta of t minus nts. That's my sample signal. And I need to convolve this with a rectangular of t over es. Now, as I said earlier, nothing is easier than to convolve with the delta pulses. So this becomes, in a time domain, sum n goes from minus infinity to plus infinity x of nts times rectangular of t minus nts over es. And this is exactly what I have here. These are the samples multiplying these square pulses, each one of them positioned at the t over nts, that's at the point nts, and each one of them having a width of ts. So they all extend, ts on each side of the sampling interval. So that's essentially just a translation of this graph. But let's look at the frequency domain. And I'm deliberately going to keep this picture here because it will help us understand what is going on. So let me take the Fourier transform. So x hat of f is going to be Fourier transform of this x hat of t. Now, in time domain, it's a convolution. In a frequency domain, it becomes multiplication. So it becomes Fourier transform of a sample signal, x bar of t, multiplying with the Fourier transform of the impulse response of your filter. Fourier transform of the sample signal, we already know. This is 1 over ts, sum when n goes from minus infinity to plus infinity, x of f minus nfs. That's our the Fourier transform of the sample signal. Remember, sampling in the time domain is the periodic extension in the frequency domain. So that's the first part. The Fourier transform of the impulse response. Impulse response is the rectangular pulse. So what is the Fourier transform? Sync. Excellent. So this is going to be sync, and it's actually going to be ts. This s was positioned in the right spot. ts times sync over pi f ts. So you have essentially this ts and ts will cancel, and then you have the product of these two. So how do I thought I was going to be able to use this, but let me redraw the picture here. So this is now, and I'm going to deliberately oversample this so that this becomes more practical, right? Now, what is happening here? I have a sync pulse that is filtering in a frequency domain. So here's how this sync pulse would look like. Right? So what do you notice here? You notice it is not doing an extremely good job, right? There are two things that bother us. First,
It's not really flat here. But that I can avoid by making Fs larger, right? Because if Fs is large, then the change of my frequency response of the sinc filter is going to be relatively small. So it's going to be flat over the area of the spectrum that are of interest to me. But what bothers us more is the fact that it's not very selective. It is letting these portions of the signal, portions of the higher frequencies go through. And as a result of that, I need to put something else to actually add an additional filter. And a simple low-pass filter, as you were suggesting, that we just do this, would actually do the job. So that's why we put a capacitor or put something else to get rid of these high-frequency variations that are coming from a sinc. This one is very appealing, and it's actually a natural way of reconstructing, because if you think about it, when you reconstruct the signal, you're sending it to some D to A converter, right? D to A converter, you give it a number, it puts the voltage out there, right? So it will give it, you give it the sample number, it puts the voltage, and it holds it, right, for some time. And then when the new number comes in, it changes the voltage, right? So this is a very common way of reconstructing the signal, because this is how it comes out of the D to A converter. But what happens is, very rarely it's left like this. You actually follow this, since the signal is now analog, you follow this by some simple analog filter to smooth out these rough edges and bring back the signal to its smooth baseband version that you started. Okay. So I'm going to stop here. Let me assign you
Problem.
Go ahead. Well, problem, right? Let me assign your. What I didn't catch it. What did you say?
Problem.
Yeah.
Yes.
So problems are 8, 1-1, -2, -3, -4, -5, 6, 7, and 8. These are the problems that exercise the material that we covered today.